I'm Ansel Foxley. I'm a lecturer in the Department of Physics and Astronomy here at UNC. That means I teach, which means I get to spend my days talking to some of the most interesting people in the world, you, about some of the most interesting ideas in the whole universe. The things that I really love to teach are these ideas where our common sense goes one way and cold, hard logic and reality goes the other way. Examples include quantum mechanics, where we learn that particles are waves and waves act like particles. Or in relativity, how we learn that a fast-moving clock runs more slowly than an identical clock at rest, which means that I could get in my spaceship and travel around at close to the speed of light for a little while, and I could come home and meet my great-great-great-great-grandkids. So truly, real life is far stranger than any universe imagined by any author of any science fiction novel out there. And right now, real people, like my colleagues in this department, are digging in and trying to unlock more and more of the mysteries of this crazy experience that we're all sharing. My colleagues are working on cutting-edge new physics and astronomy and exploring regions of the cosmos that humans have never explored before. So come with me and let's find out what my colleagues are up to.
My name is Mariana Lazarova, and I'm an assistant professor at UNC. I'm an observational astronomer. So for a living, what I do is I study galaxies, particularly galaxy evolution of quasars, some of the brightest galaxies in the universe, some of the most energetic phenomena. So we are trying to look at things that are billions of light years away from us and trying to figure out what they're doing and why they do it. A quasar is a specific type of galaxy, yes, but what's interesting is ever since we discovered that there is a supermassive black hole in the center of every galaxy, and in most galaxies these are inactive, like the one in the Milky Way, for instance, where there's stars swirling around, but there's not too much activity going on. In some galaxy centers, those black holes are super active, so they swallow up material, little gas, maybe snack on stars and things like that, and create an extreme emission in the center. And that emission very often outshines the galaxy itself. So we actually are still trying to understand why so few of the galaxies in the universe are quasars, right? Why are they active? Why are they swallowing material in such a rapid pace? And how does that make them different from typical galaxies like the Milky Way, the inactive ones? So I think one of the most exciting things about studying galaxies that I'm looking at objects that are 7 billion light years away, right? Like think about that. Like the Earth didn't exist at the time when light left these objects, and yet I'm here today, tiny office in the middle of Colorado, studying things that predate us in many ways. So removing barriers for underrepresented minorities, for instance, in physics, it's really about being sensitive to the issues that might be at play, really. So I think kind of the attention we give to our students and is what makes the biggest difference, because at the end of the day, I feel we're people. Like you go through your own struggles. You just want to make sure you're supported through those struggles, right? And I think we do that. We do that really well as a department. Like this is definitely a department that treats their students as if we're part of a family.
Hi everybody, my name is Tyler Engstrom. I'm the newest faculty member in UNC Physics and Astronomy. My research area is in soft matter physics, which is a really vibrant, fairly new field of physics. So soft matter is basically squishy stuff. So it can be soft in sort of two different senses. In one sense, it's just really thin, right? So it's easily deformed because it's thin. Like this might be a strand of DNA or another kind of polymer, or it might be a thin membrane like origami that you're folding, or a sheet of graphene, something like that. And the other sense in which it can be soft is when it has a really weak shear modulus. So examples of this kind of material are like rubber, or some colloids like mayonnaise, something like that. Or even things we don't usually think of as materials, like a cluster of honeybees has a weak shear modulus. So soft matter in fact encompasses a lot of living tissues and other living systems. I'm interested in how developing organs get into their shapes, like how your brain folds, how the insides of your gut and your airways wrinkle, how the hair follicles on your skin pattern the way they do, even the way how the ridges on your teeth come to be. So there's those processes are called morphogenesis. I have a pet rabbit, and his cerebrum, this part of the brain, it doesn't look anything like ours. It's smooth. It maybe has 1 or 2 folds, whereas our cerebrum is highly convoluted, as you've probably seen in pictures. On the other hand, my rabbit's cerebellum, a little structure in the back of the brain, it looks a lot like ours. So there's this interesting scale invariance of the cerebellum that you don't see in the cerebrum. So understanding that is an interesting question. This morphogenesis work has great opportunities for undergrads, and in fact, I've already hired 2 undergrads to work in my lab this summer. So one thing I want to have them do is extend this model, this description of the cerebellum, to a little pit that forms in the back of your eye called the foveal pit. It's where the center of your field of vision is focused. All right, and I have an idea that this pit is forming by some kind of elastic instability, and what we want to do is make gels that have the same geometry as the developing eye, and see if we can bend the gels or kind of swell them in various ways to get pits to form that have the same morphology as this foveal pit in the back of the eyes.
Hi, so I'm Dr. Charles Kewen, and I'm an astronomy professor here at UNC. So my first area of research is essentially studying starquakes. We call it astroseismology because it works in many ways similar to seismology on Earth, which is, of course, the study of earthquakes. Earthquakes on Earth can be used to learn about the interior of the Earth. They have monitoring stations all over the planet when an earthquake happens. They look at how those vibrations from the earthquake travel through the Earth and show up at different places. And that tells us about what the interior of the Earth is, even if we can't drill down and actually see it. Well, we can do the same thing with stars, that lots of stars vibrate on their surface. They have starquakes, kind of similar to we have earthquakes. And these starquakes allow us to figure out what the interior of stars are like, even though we can't see them. And so that's a really cool thing we get to do here, and it's something that we can get students involved in. You could walk into UNC today, as a student and go, hey, I want to be involved in research right now, I'm on campus. And we could get you working on something like that.
Oh, I'm Matt Seamack, and I'm a physics professor, and I teach physics. That's one thing I do. And then, what we do too, we like to play around in our research with all our students, and we get to do something with what's called the Colorado Space Grant Consortium, which gives us all this great encouragement and resources for doing aerospace stuff and all kind, which means everything. So, yeah, it goes from what you might consider like robotics and things that have to do with rockets and things like that sound traditional aerospace, but now we go all the way. We're talking about a lot of information science. We do things, been lucky to do things in audio physics, which NASA also is very interested in. And for us, and when I have my students, we're always interested in, intelligibility, but at, of course, very high sound pressure levels. To also figure out, how do I make something tremendously loud and challenging to listen to, listenable and discernible, and stuff like that. And that has to do more with loudspeaker design and especially high frequency design. So psychoacoustical things there. I'm probably not the regular physicist. I'm just someone who does stuff and loves stuff such that the physics world on this planet comes closest to dealing with those things, that I'm interested in. But my big thing is I love to just do my best to observe nature the best I can and learn from what I see. Oh yes, I'm one of those people who studies the brain. If I can get there, I don't know anything about the brain. Consciousness stuff, how do I approach it little bit by little bit this way, and seeing how the nature works that way, how the brain works, how things, and I'll be dead before I get anywhere, but it's a good ride, My students pick me up and I'm all fine. So in other words, I think the number one thing, I get to play, do research, but when I'm around these type of students, you can't ask for more wonderful things. So the big thing is being able to work with the students and just have them do their thing. And without them, there's no reason for me to be here, you know.
I am Professor Chalupka. I do a bunch of different projects, usually doing things with atomic physics and lasers and imaging. And this is a project on something called hydrodynamic quantum analogs. With this experiment, we basically look at little droplets of oil that bounce on this surface, and they basically mimic behavior that we used to think was exclusive to quantum mechanics. We can see that in a system that clearly isn't quantum mechanical. It's a classical system, and it's very accessible to us as researchers, but it has some of the weirdness of quantum mechanics. And I love weirdness of quantum mechanics, and if you can make it more visible and more easy to kind of experiment with, then that's pretty exciting. My kind of background is in really intense lasers interacting with atoms, and at the very extremes, things that students learn, it's actually kind of wrong. And if you make things really, really intense, then atoms can absorb many photons of light at the same time, and you can kick off electrons and rip atoms apart with frequencies of light that shouldn't be able to do that. So kind of take some of our very basic understanding of atoms and light in the very simplest, most fundamental way and turns them around a little bit. I think one of the biggest things that we can offer is kind of this kind of thing. And I don't mean this experiment, but I mean how this experiment came to be. And it literally came from a student who had a really cool idea. And when he showed it to me, I didn't care that I had never done it before, but I was like, we have to do this. And it's kind of taken off since then. And we've presented this work at big physics conferences and been involved in things that I would have never been involved in ever, because it's not really in my field. So I think we kind of have that flexibility that we have a lot of stuff we love doing, and if you want to do that too, that's great. But if you have some really cool ideas, chances are you're going to find someone who will take that on with you and do that work. So kind of that flexibility to meet with the students and meet their needs and their interests.
If you'd like to join us on this epic journey we call science, I hope you'll choose to do it in the Department of Physics and Astronomy here at the University of Northern Colorado.